Okay. All right. Um, Great. So I won't do too much of a previously on, but just a quick recap. So in the first talk, what we argued is that the origin of mind recapitulates the origin of life, and we said that that happens because those are fixed points um, in an information theoretic landscape, and we identified specifically what those fixed points were, and then we said how we're going to evaluate this proposal with respect to the best science in terms of origin of life. Um, and so now what I need to do for you is to provide the actual formal model. So um, that's what we're going to do today. Um, And the in order to do that, I need a basic framework. So the bill of materials are is the category of graph structured lambda theories. So in the category of graph structured lambda theories, we find all of the known models of um, computation. Uh, And this is a very interesting perspective, right? As I mentioned in the last talk, um, having this vantage point where we can see all of the models as a single mathematical universe of discourse is quite new. Usually, people do a deep dive, right? So there are lots of people who are experts in the lambda calculus. There are fewer people, but still lots of people who are experts in the pi calculus and so on, right? Lots of people who are experts in Turing machines. What I found is that in the wider, outside of the programming language semantics community, um, in the wider community, um, not so many people know about all these models. A lot of people know about Turing machines. Um, very few of them, much smaller fraction know about the lambda calculus outside of the community of programming language semantics. So being able to see all of them gives us a really interesting perspective. Um, so Uh, and but in terms of the enterprise, the adventure we're on in this series of talks, um, it provides this framework provides all the necessary entities to carry out the constructions and the arguments, as we'll see. So now I need to tell you what the category is, and what I'm going to do is I'm going to give you some intuitions and an example. To trot out the formal definition would take the better part of our hour together, and so I won't be doing that. But um, intuitively, we can think of a graph structured lambda theory, or a GSLT for short, as a Levier theory augmented with two superpowers. If you're not familiar with the Levier theory, um, if you think of a grammar like a context-free grammar or something you could describe in a tool like BNFC, you're not far off. The thing about Levier theories is they do not support languages with binders. So the lambda calculus, the pi calculus, the rho calculus, even logical languages which support quantifiers. These are all languages that have binders. And it turns out that binding is a super important compression technique when it comes to computation. So having binding available, even though it's not strictly necessary, is it's important to make things practical. So it turns out that Marcello Fiore has developed a notion of binders, which we can add to the category of Levere theories, or the categorical structure that allows us to express Levere theories. And so that's the lambda theory part of graph structured lambda theories. So this is not necessarily a lambda calculus or different flavors of the lambda calculus. It's just that we now have the ability to have bound variables, and to do all the mishigash about alpha equivalence and all of that stuff is factored into one nice place, and that's Fiore's apparatus. So the other superpower is that in addition to terms, with binders, we want to be able to reduce those terms or evaluate those terms. So we're going to use a graph to represent evaluation. So directed graphs are just another Levere theory. So to whatever is the term language for your model of computation. So the algebra, so again, I should be clear. Think of terms as representing states. So the term language with binders represents a state of a computation. So then the graph structure represents state transitions. So essentially, what we need to do is to say, for a given transition, what is the source of that transition? So which term, which state is the source of such a transition, and what is the target? Where do we go? So I'll give an example in terms of the row calculus, but in terms of the lambda calculus, a state that involves an application term where the function position of the application is a lambda term, and the argument position of the application is just any old lambda term. Sorry, the function position is an abstraction, and the argument is any old lambda term. Then beta reduction is the state transition. So basically, this gives us the categorical or category theoretic apparatus to write down all rewriting systems that have binders. And if that's not landing for you, if you're more a programmer at heart, this gives us a way of providing a description of a virtual machine, but not just a particular virtual machine, but all of them. So the JVM, the CLR, all of the virtual machines you can think of, we can write this way. So let me give an example of how to write one of these. So I just want to carve out a piece of this. So I don't know if you can see my cursor, but I'm kind of carving out. So this whole thing here is the free term language for a version of the row calculus. If we don't include the in constructor, then that is just a Levere theory, right? So it only involves sorts and products. So just to give some examples, the zero process is it's a constant, right? So it takes nothing and produces a process, which is specifically the zero process. Whereas the parallel composition takes a pair of processes, right? So on either side of the vertical bar, and produces a process, which is the parallel composition of that pair. So that's, that gives you a flavor of what's going on here. This is where binding is occurring. Notice the that the second argument of this term constructor is a continuation. It's a lambda, right? So given some names, we can produce a process. So given a function from k names to processes, we can form and the name, which is where we're going to locate that in. So this is the for comprehension. This is the send in row. So given a name and a function from k names to processes, we can produce a process, right? And that's just the for comprehension or the input construction. And then we have some equations. So that's part of a theory is equations, and the equations are just that parallel composition together with the zero form a commutative monoid. And then we have some edges. So we use E to represent the sort of edges in the graph. So here we have a two-sorted theory. So P is a sort of processes or programs, N is the sort of names or channels. And over here, we need the sort of edges, which are the state transitions. I won't really function on the run one. You can look it up in Mike and Christian's paper on native type theory. But the COM one, this is the famous COM rule. Right? So it takes some data to produce an edge. It takes a name where the input and output are going to synchronize. It takes the arguments to the output and the continuation in the for comprehension and produces an edge, right? So since it's an edge in the graph, we have to say what the input, the source and target are. So we use this funny squiggly notation here that says the source of an edge like this, right? So here, this is the n, this is the vector of arguments, and this is the function from names to a process. Right? So the source of that is an out in parallel with an in. So normally to be consistent with lambda, I write the in first and the out second, right? So function applied to arguments. But of course, because this is a commutative monoid, it doesn't matter which order you write them in. And so this is just a familiar COM rule. It just says when you have an output hitting an input where they're synchronizing at the same location or channel, then we effect the substitution of the code for the arguments for each of the variables. That's just a familiar COM rule in the row calculus. There's some other equations on edges that have to be respected in order for this to be a graph. But I won't go over those. This gives you a sense of how easy it is to write down in the language of graph structured lambda theories a given virtual machine or model of computation. So that is a very quick tour of the category of graph structured lambda theories. Almost what I've said really is what the objects are. But the question is, what are the morphisms? And when you're asking what are the morphisms in a category, another way to ask that question is to say, what structure needs to be preserved as we move around in the category? In the native types paper, the morphisms preserve syntax. So basically, they preserve term constructors, and we'll see that in a moment. But there's another. We'll note that this is too restrictive. So in particular, if I were to try to get morphisms between, say, the ambient calculus and the lambda calculus, attempting to be to preserve term constructors is nonsense, because the lambda calculus application is not commutative, whereas the parallel composition in the ambient calculus is certainly commutative. Yet there are interesting maps, say from the lambda calculus to the ambient calculus. Right, so that would be an ambient interpretation or an interpreter in a virtual machine for the ambient calculus of the pi calculus programs, right? That would be a morphism that we might want to construct. And then the question is, what does that preserve? What should such morphisms preserve if they don't preserve syntax? And the proposal is that they preserve bisimulation equivalence classes. So if you remember what we talked about last time, this is basically preserving the structure that we identified as very, very important for a theory of mind. So preserving that structure is important, and what we will see when we do that is that we therefore transport the Hennessy-Milner logic. So if I have a Hennessy-Milner logic that I've developed in terms of applicative bisimulation in the lambda calculus, and I have a Hennessy-Milner logic that I've developed for, say, the ambient calculus or the pi calculus, when I transport from, say, lambda to pi or lambda to ambient, then I will be able to also transport formulae. And that's very, very important when we're thinking about how to get from one ontology to another. Okay, so let's look at this in a little bit more detail. So I'm going to distinguish two flavors or two versions of the category GSLT. So notice when I'm using this font, I'm looking at the entire category, whereas when I'm using the ordinary font, I'm looking at objects in the category. So a particular GSLT as opposed to the category, an entire category of them. So there are two flavors, which I'll call GSLT Sen and GSLT Sem. So one is preserving syntactic structure and the other is preserving semantic structure. So in equations, what we're saying is that when we write F is a morphism from G1 to G2, where G1 and G2 are specific GSLTs, then in GSLT Sen, that means that if I have some term here, where T is the term constructor, then this equation has to be respected. So if I transport the entire term, it's the same as if I transport the term constructor and transport the application of F to each of the arguments. Whereas in Sem, it means that if U and U prime are two terms in a given GSLT, then that means that, and they are bisimilar. So we use this squiggly thing for bisimilarity. So what does that mean? So remember, we have this graph structure, this kind of graph structure. And what we're saying is that the two graphs are bisimilar. So when these graphs are bisimilar, then that implies that when we transport the graphs over into the other GSLT, that those graphs are also bisimilar. So this is the preserving of the bisimulation equivalence class. And as I said, this ensures that we faithfully transport the corresponding Hennessy-Milner logic. So I know this is a lot to take in. I'm going to stop here and see if there are questions. Yeah, I mean, it's going to be an interesting moment because maybe not everyone here is a category theorist or a type theorist or a programming language semantics person, but I'm willing to field any and all questions, but if some of them have to do with basics like what is a category, I will have to defer that to some other out of band conversation. So questions?
I have just one question. I'm not sure if it's basic though, but I'll try. But I'm happy to be deferred to something else if that turns out to be a basic question. But when you define this theory on the previous slide, I guess, if you could go back, and let's say we have here, right, and let's say we have something like out. We have let's call it a signature, right, or type of it. But where do we, or do we ever need to have a semantic? I mean, how out should work?
We do. Out doesn't work by itself. Only parallel composition works in the same way that only application in Lambda works, right?
Okay.
If I have a lambda If I have a lambda term, that doesn't do anything. If I have a variable, that doesn't do anything. It's only if I have an application of a lambda term to some other, I'm sorry, of an abstraction to a lambda term that I get beta to apply. Same thing here, right? Out doesn't do anything by itself. In doesn't do anything by itself. But when I put an out next to an in parallel composition, that can move, that can wiggle.
I see, but if out takes a name and a bunch of processes and produces a process, picks basically the choice, right?
No.
Then
No, this is literally just forming the output process. That's all it's doing. This is a term constructor or a
oh,
set.
I see. So there is no question of how to pick the process
No,
because there is
no,
no picking. It just forms a process.
it just forms
Yeah,
a
I
process.
understand.
Yeah, this is
Right.
in bang q, right? That's all it is.
And if that structure appears in another equation, let's say in com rule, then it's
Yeah,
it's defined. Okay, yeah, okay.
yeah.
Now I get it. Thank you very much.
No,
That's what
I'm
what
glad
I
you asked that
missed.
question. That's yeah. Switching back and forth between all these distant presentations of the same material can get quite confusing. So yeah, no, I appreciate your question.
Thank you very much.
Let's see, where are we? Okay, right. So that's basically GSLT Thin versus GSLT Sim. So now, how am I going to get all the things that I need from the previous talk? Well, it turns out there are a bunch of functors that live on GSLT, and if I don't put the subscript sin or sim, that means that the functors live on both categories. So there's one functor that's being developed largely by Mike Stay. Mike and I have been working on it together, but this is mostly his work. Where he lifts the lambda cube construction, which we referred to in the last talk, to the entire category of GSLTs. So he's at the point now where we're just about to start coding that functor up into software. I am not really concerned with all the vertices on this cube. I recommend taking a look at the Wikipedia page on lambda cube. I am interested in the extremal point because the extremal point is where types become effectively terms, right? And that's the point at which programs can do science. So here is our GSLT. So so you want to read this now is we can lift all these relationships, we can lift them out of their home in the lambda calculus and now put them in their rightful home, which is the galaxy of graph structured lambda theories. And so here would be some GSLT, and up here is a GSLT that's been decorated with types, and those types are effectively first-class citizens. So they're also terms. And the reason I say, just as a reminder, I say that now programs can do science is because of the argument I gave before. So the only thing a program can see is the universe of computations. Therefore, the only ontology, the finest possible ontology a program can ever observe is the bisimulation equivalence classes. The bisimulation equivalence classes correspond to the Hennessy-Milner logics. The Hennessy-Milner logics correspond to the types generated by this cube here. And we have all of those steps worked out in this functor. So that, and when the types are available as first-class citizens, now the programs can make a hypothesis in terms of the only ontology they can ever see, aka the types, about their environment. And they can interact with their environment and get new data, and thereby potentially change the types in response to the data they've received, which is the equivalent of changing a hypothesis about the structure of their environment. That's how programs do science using this constructor. And so So this is the second fixed point. Now in this talk, we're mostly going to be focused on the first fixed point, but this is the second fixed point. This reiterates the first fixed point, which we're going to be talking about in more depth. This language from the first talk, where I do a 2-level type decomposition of this nice, beautiful Hennessy-Milner style type system for the row calculus. This thing here, that's the result of running Mike's functor. So running Mike's functor generates this domain equation. So that's why this apparatus is the kind of apparatus we need in order to describe the thesis in a relative level of formality from the previous talk. Okay, so now you, yes, go ahead, Marcin.
I have another question. So when we take a look at the lambda cube, then most languages that we know and love, say Scala or Haskell, are not in the realm of the right-hand side. They are more in the realm of lambda omega or f omega, right? So
that's right. Yes,
they are not dependently typed languages, or at least not fully dependently typed. It can be simulated, yet the type and term dependency is usually not there. So what does it say about those languages in terms of this theory of mind, or programs doing science? Does it mean that programs written in those languages cannot be used to describe mind, if that's the right expression, or cannot do science because they lack this?
That's a great question. So let's understand how to apply this functor. So what we would ask is, give me an untyped version of Scala, just the core of Scala that doesn't have any types at all. When you give me the core untyped Scala, we will now generate for you 1, 2, 3, 4, 5, 6, 7 type systems, the extremal point of which will be a dependently typed Scala, right? So part of what has plagued Scala is the fact that the type system was handcrafted, right? So up to Scala 2 point whatever, 2.15 or something, I can't remember where they jumped over to 3.0. All of that stuff was not only handcrafted, but it was unsound.
Right. That's another argument.
And that's why they did Dotty, right? So was to be able to simplify those calculations so that they could get soundness to go through for Scala. So here we're saying, hey, you don't have to do all that. We'll just generate it for you. Give us a clean operational semantics, and we'll give you the rest.
So you're basically saying that all this work that, say, Simon Peyton-Johnson and his crew put into F omega is basically, well, maybe not a waste of time, but they could have waited for these results.
That's correct. Now, on the other hand, I think that their work could inform our work in the sense that they didn't just work out an implementation. They worked out optimizations, right? So there's probably a whole bunch of optimizations that we can just lift directly into this framework, right? So a bunch of transformations that we can apply to the hypercube functor, which will give us better implementations. But the nice thing about that factor is, the nice thing about structuring the software that way is that it now works for everything. Right? Now, it may very well be that some of the optimizations critically depend upon, like in Simon's case, it critically depends upon the fact that he's working in Lambda as opposed to, say, Rho or Pi or whatever. But some of those optimizations may be generic, in which case they could be applied across the entire galaxy of GSLTs? So great question. It really opened up a lot of stuff. Thank you.
Thank you very much for the answer, Kim.
Okay, but another along the lines of the questions that you're asking about, we recognize that in the real world, things aren't always classical. Things aren't always crisp and deterministic, or crisp and non-deterministic, but the non-determinism somehow is supplied by races. I've been working with Jonathan Worrell, and again, it's mostly Jonathan's work, to provide another functor on the category of GSLTs. So you give us a graph structured lambda theory, and we hand you back either or both of a 1 or 2 norm stochastic version of that rewrite. So what we're saying is that we'll now give you probabilistic rewrites, and the kind of probability theory that you use can either be 1 norm probability theory, which is our usual notion of probability, or 2 norm, in which case it's quantum. And the way we do this modification of the graph structure rewrite theory allows for Gillespie style simulation in place of execution. So rather than run it, we can simulate stochastic versions of the execution using a generalized form of Gillespie's algorithm. This is very important if we want to talk about other models of computation besides what people might consider toys, like the lambda calculus. If I want to actually model things in the real world, I have to deal with stochasticity. And if I want to model quantum computation, I have to deal specifically with 2 norm stochasticity. And this functor says how to do that generally for the entire category of graph structured lambda theories. And this is why I say GSLT, the category of GSLTs, allows us to reason about all known models of computation. That's important. Now, it also turns out that we can compose these functors. So we can say, hey, let's start with some GSLT that is defined crisply. Let's make it stochastic, and then run the type construction on it. So we can now embody, just through the composition of these functors, programs that do science in an uncertain world. That's critically important, right? If we want to do this for real, we have to allow the programs to reason in the context of uncertainty. And we want to do that in a manner that is completely prescribed, right? So these functors completely prescribe these processes. So finding this fixed point or finding this fixed point are entirely determined by these algorithms. In the third talk, just to give you some foreshadowing, I will show that there's a fibration over the category of graph structured lambda theories, where the fiber or stalk over each such graph structured lambda theory is the tower of hypercomputation that Turing identified in his PhD thesis. So Turing was well aware that there was a computation much more powerful than Turing machines. So in his thesis, right, there's the above Turing machines, there are so-called hyper Turing machines that can solve halting problems for these guys, but they can't solve their own halting problems. And then above this is hyper Turing machines And they can solve halting problems for these guys, but they can't solve their own halting problems. And on up it goes forever, corresponding to a tower of large ordinals. And what we want to say is that Turing's results lift through the entire galaxy of graph-structured lambda theories. So sitting over top of each one of these is this tower of hypercomputation, and this will become important when we start exploring questions like, hey, does this mean that mind is completely programmatic? Does this mean that there's no room for creativity? There's no room for, you know, angels and demons and all kinds of strange phenomena. And we'll be able to at least put forward some proposals with respect to that. All right, but now back to our program at hand. I'm going to have to move somewhat quickly because we've only got 19 minutes left. So we have to pick out a special class of GSLTs, which we call the interactive GSLTs, to start talking about life. So these are ones where the left-hand side of the rewrite rules are composed using a binary operator. And we'll denote abstractly that binary operator with circle dot, but understand that this is an abstraction, right? When we map it into specific GSLTs, like the lambda calculus, the circle dot is application in SKI, the circle dot is application in the pi calculus, the rho calculus, the ambient calculus, and a bunch of others in that family. The circle dot is parallel composition. But essentially, what the circle dot does is allows us to divide the world, to divide state. Remember, these terms provide you an algebra of state. They represent state. And we're now saying we can divide the state into a program and its environment. Or, in the case of commutative operations, a program and its environment, right? So when the circle dot is parallel composition, P is an environment for Q, and Q is an environment for P. Right? So that's a very interesting point. And for interactive GSLTs, or IGs for short, the hypercube functor defines an algebra of observations. Somebody raised their hand? Is that true? No? Okay. So what do I mean by that? Well, suppose that you know, hypercube has generated some type system for us, and we know that P is of type T, we know that Q is of type U, and we know that R is of type V. And further, suppose that we know that when P interacts with Q, that goes in a single step to R. So this is the state transition. Then that allows us to conclude that Q is of type after we see T, it is possibly the case that we see V. And after and P is of the type after we see U, it is possibly the case that we see V. Or probably the better way to put the possibility modality so it's more precise is, it is possibly the case that after T, V, or it is possibly the case that after U, V. Now notice that the difference in the angle brackets, that's because this operator might not be commutative, right? So this represents the left-hand side and this is the right-hand side. When this operator is commutative, as in the case of parallel composition, these two operators coincide. This is the modal logic I was talking about. This is the revamped version of Hennessy-Milner logic for which we have this bisimulation equivalence, you know, characterization. So the modal types completely characterize the bisimulation equivalence class. It's also instructive to rewrite this in a couple of ways. So we can look at possibility versus necessity. So when Q is of type possibly after TU, that's the same as there exists a P of type T, such that when I put P, when I interact P and Q together, whenever they go to R, that means that R is of type U, right? So P is the evidence, and here we're showing what the what the evidence is, and we can see that there exists requires only finite evidence. Necessity requires potentially infinite evidence. Instead of there exists a P, I need all of them, right? So if there are potentially infinitely many, then this is potentially infinite information. And so these kinds of witnesses are often hard to come by, right? So it's very much reminiscent of topology, right? So in a topology, I demand that I only have finite conjunctions and infinite so finite intersections, infinite unions, right? So that is telling us where this constructive divide lives. So the hypercube functor only generates this bit and does not naturally generate this thing or a negation, such that we could define via De Morgan's laws necessity in terms of possibility. We have to go all the way to native types to get these two to line up nicely. And that's because of this finitary versus infinitary information. Now, armed with this, we're now going to do, we're going to set up to be able to do physics and build the life meter that Sarah Walker and Lee Cronin have been going on about at some length, but to build it in the category of GSLTs. So that's what we're about in this talk. And hopefully we can get that done in the next 13 minutes. So what I'm going to say is that an interactive GSLT, so an IG, supports a collection of combinators, which we will write com of G. So com of G is going to be a subset of the programs in G, such that every program in G is bisimilar to a program made entirely by interactions of the combinators. So in symbols, right, if com G, oh, that should be a capital G, sorry. If com G is some collection, some subset of programs of G, then for any program in G, there exists some collection of combinators such that when they are interacting together, it reproduces the behavior of that program P. So we're going to abbreviate an IG with combinators to an IGC. So let's give some examples. SKI or combinators for SKI. Oh, big surprise. The image of SKI under its translation to the lambda calculus, so that's a collection of lambda terms now. Those lambda terms are combinators for the lambda calculus, right? That's just reinterpreting well-known results. The image of the row combinators in the row calculus are also combinators for the row calculus. Again, that's just reinterpreting well-established results. The intuition you should have is that combinators are the elementary particles of every IGC. These are the smallest gadgets where all observable behavior arises by interaction. So these are the quarks, leptons, and gluons of the computational universe, which I think is kind of cool. But now, armed with this apparatus, we can transport the definition of an assembly index to an IGC. So if you take any program, you atomize it. Well, what does atomizing do? It delivers back to you the set of combinators such that when you do a big interaction over this set, or let's call it a collection rather than a set, because it might be a multi-set. So you have some collection of combinators such that when you put circle dot between them or amongst them, then it's P is bisimilar to that, right? So effectively, we've just what Atomize does is it emulates, like a mass spec, right? You give it a program and it smashes it into its constituent components. Right now, we can run the assembly index algorithm on the atomization of P. Right? We grab two combinators or whatever in combinators, we put them in interaction. We formed a new gadget. We put that back in the pool and rinse and repeat until we have reproduced P. And the shortest path to do that is the assembly index. That's it. That recapitulates the assembly index in the category of GSLTs. I should point out that in this definition, this this collection may not be unique, right? So that's why we might have lots of different paths to assemble P, right? Okay, but now remember, there's this other thing that we need for our life meter, and that's the copy number. So there we have serious problems. So I argue, as I mentioned in the last talk, what is the frame or scope in which we can make sense of copy number, right? Because if the frame or scope is the entire universe, then copy number is not well defined. Not even a scientific theory. We can't test it because we can't explore at least given our current state of affairs. Maybe after AGI or ASI, we can view all of the the entire universe, but certainly from where we are as humans right now, it's hard to make sense of counting all the copies of something in the entire universe. But it's worse when we're in a mathematical domain, right? At least in the physical domain, we have some ghost of a chance of exploring the entire extent if the physical universe is finite in size. But in a GSLT, there are an infinite number of copies of a program. And worse, there are an infinite number of copies of a population of programs. So how are we going to define a natural notion of scope in which to restrict our counting? And the problem appears like it gets worse and worse the more you try to make it practical. For example, in the assembly theory papers, they use sets to calculate copy number, but sets don't admit copies. The union of the set containing the letter A together with the set containing the letter A is the set containing the letter A. Sets erase copies, right? So there's several mathematical tricks for dealing with this. There's multi-sets and disjoint unions and all kinds of things. All of them involve tagging. You tag the copies. So that's kind of interesting because now what happens if I have like two different scopes in which I'm counting, right? So I'm counting all the lemurs in Madagascar, and I'm counting all the lemurs in South Africa. Right? And now I want to combine those two scopes, right? So I want to somehow, in order for that operation to be compositional, I need to add structure to the tags to represent that I've now gone up a level in terms of the counting scope. So now tagging starts to get structure, right? And that's very problematic. Why is that problematic? Well, because if tags have structure, what sort of structure is this? Is this also an object for which we need to calculate an assembly index? Do we need to start worrying about the copy number of tags? Does that mean that we're in danger of an infinite regress? So that's a really interesting puzzle. And it turns out you would never have guessed it. This is where our first fixed point comes in. Rho is the smallest version of the lambda calculus in which terms are collected in multisets, and the tagging infrastructure for the multisets are just row terms. So let's make that crystal clear. A typical row program is a multi-set of functions unioned with a multi-set of arguments. where the tags for the multisets are just terms, row terms. So the function is lambda y s1. The tag is at r1. The argument is q1. The tag is at p1. This
So
is literally
quoting is essential. Quoting is the
yes,
most vital part in it. Huh.
that's exactly right. That's exactly right. That is the fixed point. Yeah.
Because
Okay.
quoting, as I see it, is like a final or ultimate introspection, right? Or gives you
Yes.
that, and that's
Yes.
seemingly very important. Yeah.
Yeah. And it turns out that it's not specific to row. The only thing that picks out row is that it's the smallest thing by way of lambda. Like if you went by way of some other GSLT, you can still get quoting. Um, there's some subtleties around whether your model uses substitution or not, but the main point is that the quoting part is the fixed point. So locations give you the quoting gives you locations, and it gives you programmable locations. And that's really what you need. And that's why, like, both quantum mechanics and general relativity are so hard, because locations are being managed by matrix arithmetic in those theories, right? And they're trying to do things where the communication topology is changing, for example, in entanglement. And matrices make that exceptionally painful. Whereas quoting gives you the right apparatus to manage this shift in the communication topology.
It's
And
that's something. That's mind blowing. Yeah. Thank
isn't
you.
that cool? Isn't that very interesting?
It's
So
very cool. Yeah.
I'm going to run over by 5-10 minutes. Can people stay? Okay. All right. Thank you. I appreciate your patience. All right. So more generally, so if we look here, what we've done is we've given an extensional set of tags here and here, right? So I've written down for you all the tags. Now it may be that there's sets of tags which I can't write down for you in a finite amount of time if I write each tag down individually. But if I could describe the tags in terms of their inner structure, and notice that the tags do have inner structure, that was the point we were just hammering home. So since they have inner structure, we can write a recognizer for that inner structure. And that is exactly the typing that is generated by the hypercube functor. And if you run the hypercube functor on row, you get namespace logic. So, um, so in general, we define a frame of locations is a namespace. It's just a collection of tags, and that tags can either be given extensionally or intentionally via a namespace logic formulae. And then we calculate a copy number of a parallel composition of programs, or a collection of interacting programs, right? So our elementary particles relative to a namespace. I won't break this formula down for you, other than to say that's what this is doing for the case of row. For the case of row, we can now define copy number. We can do it more generally for GSLTs, but now we have a notion of copy number that and I want to point out that this calculation, this way of, you should think about this in terms of differential geometry. This is a manifold, and this is a chart that you lay over the manifold. The problem with differential geometry is that it's not compositional. I can't compose the manifolds and compose the charts, right? That's why you have this weird overlapping differentiability issue in differential geometry. Here, we've sorted that out using compositionality. So the weirdest thing of all, I did not expect this at all, is that if you actually push GR to its logical conclusion, out pops DNA. As if you remember in the last talk, what I said is that location as code is DNA. And now I will make that argument even crisper. We just have a few more slides. in order to make that crisper, let me remind you the other origin of life scientist that we were following. His work was Eric Smith, right? So the question is, now that we've built a life meter, what are we going to apply it to, right? So, and that question basically corresponds to inside GSLT, what looks like the prebiotic geospheres, right? And how are we going to push them far from equilibrium, right? So the idea, if you recall correctly, is that you know, the prebiotic geospheres, so the atmosphere, the lithosphere, and the hydrosphere, they're being pushed way. The chemistry of those things is being pushed way out of equilibrium because they're sitting in proximity to the sun, which is just pounding on that system with lots of energy. So where is energy in this model? Like we don't have any energy in the system of programs. Guess what? We actually do. There's another functor on GSLT that provides a way to model energy directly. We could look at it in terms of, well, a system that's in equilibrium is either you can't reduce it, or it's in some kind of steady state cycling thing, right? And then outside of equilibrium either means it's in the process of reducing, or it's in the process of getting to one of these steady state things, and that's a way to do it. However, this way makes a lot of that, like once you start to do the calculations that way, it's more complicated. And this is a way to factor all those calculations into one place. So let me say what those calculations are. Okay, so I'm going to, and remember this idea of conserving energy and being energy bound, that comes to us from physics. We don't have anything to do here. Like we don't have to explain that, right? The physicists have to explain that. We're just trying to say, if we had physics, how do we get life, right? So I don't have to go to the bedrock of why there is energy. I just have to say, here's a model of energy. So it turns out that we can model.
Sorry to interrupt. Sorry to interrupt
Yeah.
you. But if someone wants to be nitpicky, then in expanding universe, it is said that the energy is not conserved when you look at the universe as a whole. So
Yeah,
how
that's an
would you?
interesting point.
So how would we address that?
We can this model accounts for all of those things. It has to do with how you set these rules up. In fact, in this model here, energy is not actually conserved, it's consumed. But that's because what's really going on is at the level of organisms, it appears that the energy is being consumed, but really it's just being converted into a different form. Right. So I haven't modeled the conversion to a different form. But we can do that. So we're basically going to write energy as a kind of resource, and we can have interacting copies of stacks of resources. And whatever that resource is, we don't know. Like this is the ground of the resource, it could be a photon, it could be an electron, whatever it is. And then we can combine those resources. And there may be multiple different kinds of resource that we utilize. So again, we're doing this. What we're going to do is, given an interactive GSLT, there's a functor on the interactive GSLTs. So if P and Q can interact themselves going to R, then now we're going to say that they require a resource to do that. So if there's a stack of resources that has S on the top, then we go to R, still requiring S, and S has gone on, disappeared from the stack. If P and Q require an S1 and an S2, so two different kinds of resources, and S1 is sitting in one stack and S2 is sitting in another stack, then we can go to R, and those resources have been popped off the stack. If if it requires 2, and we have an S1 and S2 sitting on top of a single stack, we can go on. Now, here's the 2 interacting ones. So the way to think about this is the boundary of an organism, right? And this is the energy it needs to take to have a reaction going on inside the organism. This is interaction between 2 organisms, right? So P requires an S1, Q requires an S2, but P and Q interact with each other. So if I have the and of both resources sitting on a stack in the environment, we can take that step. Notice what happens. P and Q effectively become entangled. After that happens, they're stuck. And we can modify these rules with a variety of different policies, but these are kind of the simplest ones. And then again, if P and Q could interact, but now P requires an S1 to do anything, and Q requires an S2 to do anything. And if they're sitting on 2 different stacks, we can pop off both resources and keep going. So this is a very, very toy model. It's a very simple model, but it shows you how, given an interactive GSLT, we can turn it into an interactive GSLT that requires energy to do anything. All right. Now, notice that when an interactive GSLT with combinators is Turing complete, this can be translated back to a version without tokens. So we had the version with tokens, we can translate them back to a version with tokens. And notice that flow allows us to get the inverse of this thing, right? So just going the other direction is really just flow. But there is a difference, right? Because all the things in flow terminate. Right? All the things in the image of flow terminate. Why? If you have a finite set of resources, they stop. Even if there may be reduction steps, they don't keep going. What does that mean? That means that we're well, I'm going to hold off onto that. But basically, you can see what's happening. The finite lifetimes is implied. But we're interested. So now we can define an inside and an outside, right? So the outside of organisms, programs in the image of flow are the organisms, like in the rules, that eat energy directly. So these organisms eat energy directly. They sit on the outside of our programmatic or information theoretic geosphere, the biosphere. But now the things that sit on the inside are programs that eat other programs. So in Rho, we can now model this. So the metabolism eats energy directly. Now, again, this is a simplification. You would have many recursive steps. But in the first step of this recursion, the metabolism is a version that eats energy directly. Now the program interacts with its environment, gets a program that it can eat. It then runs that into an energy consuming program. So potentially it has energy associated with it. The metabolism eats the energy and gets rid of the stuff that isn't interesting, right? So it leaves that behind. That's the refuse, and the energy is what the metabolism is consuming. This is digestion. Now, we're only interested, though, in those programs that keep going, right? So it needs to be the case that metabolism eventually produces a continuation, right? So I've got a P that's parametric in its environment, and then this metabolism better continue the behavior of P, right? So we're only interested in the autocatalytic versions of these. Well, where do they come from? They come from fixed points. So this is the Rho version of the Y Combinator. So it's a Y Combinator in a concurrency setting where we have autonomy. So let's look at it. Regenerate, what does it do given a channel X? Well, it waits at X for some program, starts running the program, and then sends the program back along to the channel X. Notice that the assembly index of this gadget here is tiny. we will stumble on this again and again and again in a random exploration of structure. We will generate this almost immediately. Once we've generated this, then it's very, very small number of steps to generate this. Right? So what is this? Well, we take the regeneration of X in parallel with some program P. We don't care which program it is. And we send that on X. And we do that in an environment where regenerative X is lying around as a chemical in the mix. This will auto-generate infinitely many copies of P if we didn't have resource constraints. But in the case of a resource-constrained situation where you require energy to make computational steps, this is a terminating regenerative program. This is an organism with a lifetime. Moreover, in the case of Rho, we'll just focus on Rho, but it's even more in your face in symmetric versions of Rho. But in Rho, the forecomprehension is the egg. We already find the genetic apparatus. The forecomprehension is the egg. It's waiting for genetic material. Why do we say this is genetic material? Because we're only receiving the code. We receive the code of the argument, not the argument. If I do a star on the Y, like I did in the regenerate protocol, right? Then that's constructing the gadget from the code. That's building the gadget from the DNA. I receive the code, and over here, what happens? Well, this is the sperm. I'm passing along genetic material to be inseminated into the egg. It's already there. This is gamete fusion. And then when this evolves, that's the, like in the case of a human conception, this is the, the blastocyst, beginning to split and form, the organism. So it's already present in the basic way in which we do computation. It's part of the fixed point. All right, so in summary, we see a population of energy-constrained programs. There is a division of such a population into an inside and an outside, and there is a conservation of the metabolism loop. This is a fixed point of what we will find. In other words, all the key features identified by the entire biosphere, where Smith says, hey, look at the entire biosphere for the features of life, all those features show up as fixed points in these energy constrained GSLTs. Just a few slides and we're done. Okay, but now we can apply our notion of assembly index and copy number to this population of programs. In fact, what I want to argue is that the assembly index is really a proxy for this more detailed picture that emerges from energy constrained replicators. Like once you realize that you're only interested in the energy constrained replicators, right? That forces a bar. You've got to cross a certain bar of complexity, right? And so the assembly index is going to be at least that high. That's what's going on with this, why you want assembly index. And the reason you need high copy number, it falls out of basically a version of the law of large numbers. If you don't have sufficient copies, there's not enough material to do sufficient structural exploration. That's why you need the high copy number. All right, so that's a lot to digest, and I know we're way over time. I will, I'll leave it here, but in the next talk, I'm going to do two things. One, I'm going to talk about how the attractors are, how the fixed points are related to the attractors. So I'm going to complete that picture in a more formal way for the complex systems or dynamical systems view of this. But then I'm going to focus a big chunk of the time on this hypercomputation part. There's cool stuff that happens when you look at this hypercomputation vibration over GSLT. So that's it. I know I'm way over time, but if there are any questions, I'm happy to field them.
I'm trying to wrap my head around this, Greg, and the notion of a vibration as it relates to these GSLTs. So this is almost as if there's a manifold or a surface, a topological surface that these all then map to computationally, and then we should be able to then do things like figure out what the what is that von Neumann entropy of a system is if we relate it to physics in a computational sense. Do I have that right?
Yeah, I mean, you should think of the GSLT as the base of the vibration, and then the hypercomputation is the fiber above it. That's the way to think about it. And yeah, not only can, I mean, speaking of von Neumann, not only can we define a variety of notions of entropy, we can also give a complete account of constructor theory, right? If you go back to my notion of interactive combinators, I can say what it means to have it when a GSLT has a universal constructor.
Wow. Okay.
Right. So instead of this just being like a proposal from von Neumann and people like Chiara Marletto and David Deutsch, saying we'd like to know the answer to this question. For the category of GSLTs, we can answer the question completely.
Okay. Wow. All right. This sounds like it has broad implication then. Thanks.
No, thank you. Good question. All right. Well, if that's it, I really appreciate your time and attention. I thank you for the questions. I hope everyone, if you celebrate Christmas, has a wonderful Christmas. And the last talk will be a couple of days after Christmas.
And Greg,
thank you. Yes.
If in the last talk you could just point out 3 implications, social, political, commercial, economic, whatever it is, about the assimilation of these insights, what will a thoroughgoing assimilation of these insights transform in the way we live? If you can come up with a few very practical examples, I'd like that.
Sure, happy to do that. Thank you for asking. All right, folks, have a good weekend, and look forward to seeing you on next Friday.
Thanks, Greg. Happy holidays.
Happy holidays.
Bye.
Happy holidays. Bye.